Well, good morning, chemistry team. Put your geometry hats on. So this video and the next one, we're going to be looking down at crystal lattices. So we're looking at crystalline solids specifically. We're going to apply mostly to metallic solids in this one. So we're looking at atomic solids. We did covalent network solids in the last one. So we're going to look specifically at metallic solids, but this doesn't only apply to metallic solids, but it's mainly applied to metallic solids, right? So if we picture atoms as spheres, right, how are they going to fit together in different metals, right? A real generic way to think of it is just take a, like a box and pour marbles in it, right? How do those marbles stack? Or if you go to the store and you see a bunch of oranges stacked together, right? There's little holes in between them and stuff. This is a real basic way to think about how these metal atoms place together. And we'll look at that in more detail in the next video. But what I want to look at today is this thing that we've mentioned before called the unit cell. So if we look at solids, right, macroscopically, we see one particular thing. And a lot of times, you'll see the, flat edges, sharp points and edges. You might see like a kind of a cubic look to it, or maybe a hexagonal look to it, or something like that. A lot of times that look is just a result of a pattern on an atomic level that's repeated in 3 dimensions. Now, what is that fundamental atomic pattern for how those atoms are together? Well, that's the unit cell, right? There's a lot of them we're going to look at on the next board here. But basically, you can just look, a lot of ways you can define it. It's just the fundamental atomic arrangement that's repeated in 3 dimensions. So my buddy Price, builds homes and retrofits things and whatnot. So he's real good at, he can lay tile, he can remove walls. So can I know several people that can do that. But if you're laying tile down, that's 2-dimensional, it's flat. And it just, you take this tile, put it on the ground, put the goop, whatever. I don't build things. I can't do that. Some adhesive thing, it's like a paste or whatever that sticks, and then you put the grout in between them, and it repeats in 2 dimensions on your floor, right? Well, imagine having a cube that you repeated in 3 dimensions, kind of like this. So take a look in red here. This is what we call a unit cell. It's the most fundamental, smallest pattern that repeats itself. And then you just, like on your computer, right-click, copy, right-click, paste, right? Copy, paste, copy, paste, copy, paste, copy, paste. And this is just, you can sort of see it, and this would extend out towards you, away from you, into this, what's called a lattice. Now, I happen to have drawn a cube here, because that's the only one I can draw. Geometry was not my best math, right? I was more of an algebra, trigonometry kind of guy. But I would do this on driveways, when my kids would take chalk and write all over. So I'd be drawing patterns, and do, different equations, just having fun. But, sometimes I just draw a cube, and then my natural tendency is to draw another cube and then another cube. And I'm just repeating those cubes over and over. So you can see how they're sharing these points here and these edges. So here it is where I've got, the one here, one left, one right, one above, one below, and I can have one coming at you, one coming away from you. So can you see how that gets pretty crazy? But if we can hone in on just that unit cell and where the atoms are, we'll ultimately be able to calculate the densities. If we know how many atoms are in that unit cell, and if we know the volume of that unit cell, we can convert the number of atoms to mass. We can get the volume if we know like the edge length, especially if it's a cubic lattice like this, right? Because the volume would just be, the length cubed, correct? So if we know the mass and the volume, boom, we've got the density, right? We're going to only focus mostly on cubic lattices. We'll briefly look at one with a hexagonal lattice, but there's 7 main ones. Let me list those up on the next board for you real quick, just so you are aware of them, and we're just going to focus on the simplest one. You good with that? You probably are. You don't have a choice. Before we move on to the next board, I snuck into my son's room and grabbed a few things here. I tried to get ones that were fairly obvious. This is pyrite. Can you see that cube-like looking thing? Right there. I think right there you can see it the best. But you see you got that like a cubic structure to it? Well, this is macroscopic. That's just a result of a cube unit cell repeating in 3 dimensions, right? Till you can see it, and you can kind of see it. So a lot of these minerals and elements have stuff like that. And then this one, can you see the kind of a hexagon there? right? It's definitely not cubic, right? So you see the results of these and go, oh, I wonder if that has maybe a hexagonal unit cell. Whoa! So let's take a look at those 7. Let me erase this. This is the easiest one to repeat. The other ones I'm not going to, all right? So let's look at the 7, and then we'll get in some details, counting atoms and, what are the volumes and all that fun stuff. All right, took a little digging to get through this, but types of crystal lattices and I'm not gonna, for my class, not gonna test you on these. Only the ones with stars, we're gonna look at some examples, okay? This is not a class on geology, all right? So we've got cubic, which would be the main one we focus on, right? We like cubes, easy to get the volume of the cube, those kinds of things. Many, many different metallic elements have that. Iron, copper, nickel, I could go on and on and on. And you can get some of those periodic tables that show all the elements with the different crystal structures in them. It tells you what type it is. Tetragonal is another one, right? What the heck is that? Protactinium? God, I gotta love that one. Tin, indium, things like that. Those have a different type of crystal structure. Monoclinic, right? The only metallic one I could find real quick was plutonium on that one. A lot of minerals. I'm just trying to focus on metals, but a lot of minerals will fall into these categories. Orthorhombic, you may have heard that term before. Gallium, neptunium, uranium. Rhombohedral, and these all have to do with the angles and the lengths of the sides and whatnot. They get a lot more complicated with these. Rhombohedral, so I saw samarium, bismuth, antimony, a bunch of those ones. Hexagonal, put a star next to that one. We're going to look at one example of hexagonal. We're going to look at 3 examples of cubic and 1 example of hexagonal, so just 4 for us. Good? All right, and we're only going to dig into details on 3 of those. So titanium, zinc, holmium. And then triclinic, I had trouble just off a first glance finding any metallic elements that had a triclinic crystal structure. But a couple of minerals, turquoise you probably heard of, a microcline maybe. So kind of fun stuff. So let's zoom in on the stars, my friends. Let's take a look at these simple, we're going to look at 3 different types of cubic lattice unit cells. And the simplest one, called the simple cubic, right, unit cell, it just has the atoms at the corners, right, of the cube. You see that? This isn't a great representation of it because these represent the centers. What it really looks like, these are actually touching, right? So these are actually touching. So if you look at the face like this, see the atoms actually touch along. So it looks just like 4 atoms stacked together. But what we tend to draw is just the centers of those, so it cleans it up a little bit. Hard to draw the cube in 3 dimensions with that, showing like a space filling model. So usually we just draw a cube and then put a center of an atom at each corner, right? As you can see, nothing in the inside there. And then this repeats in 3 dimensions. Copy, paste, copy, paste, copy, paste. 3 things we're going to be after based on this, right? How many atoms are inside that? Can you see how the corner is not completely inside the unit cell? Only a part of it is. So we want to go, well, net, how many atoms are actually inside that unit cell? Only a portion of each corner is. We're going to have to figure that out, doing some fractions. I want to know what the volume of this unit cell is in terms of the radius. Can you see how they touch here? Radius, radius, right? So I'd like to get the volume, or in this case, since the volume is just the length cubed, what's the edge length in terms of the atomic radius? I'm kind of interested in that. So that would give me the volume, the number of atoms in the cell. From those, I can get the mass and the volume and the density. And then something called coordination number. So if I just pick one atom, how many other atoms is it in physical contact with, right? Because there's obviously some space in here. So let's look at those 3 things, right? Number of atoms in the unit cell, net, volume, right, in terms of radius and edge length type terms, and then coordination number. Let's do it for this. So I'm going to draw, what I'm going to do is kind of hard to see for the simple cubic. I'm going to take that simple cubic like I did on the last board and repeat that. It's going to take me a second. I'm going to draw that. If you want to do that, you can see it. And what you need to do is stack enough of these together to see how you get one complete atom. And that'll tell you how much of that atom is inside the unit cell and how many other atoms it touches to get some key information we need. See if you can do that. This takes a while to draw. All right, so I tried to redraw in a more simplistic form, taking these simple cubic cells and just stacking one up, one to the right, one to the left, one in front, one in back. But I didn't do the ones in front. All right, so just take this unit cell, repeat it over and over and over, and let's focus on just one of these atoms in the corner, that blue one right there, that in the center. Okay? So if I took this simple cubic cell, right, it'd be this one here. And then if I put another one next to it, right, that is shared by these two and these two. So you got 4 total, right, that are sharing that in the middle. And then you need another 4 in front, which I didn't draw. So we need a total of 8 cubes that all touch in that one center point, right? So I do a total of 8 cubes, and they'll all share that, which means there's 1/8 of an atom inside that unit cell, which we're going to be dealing with. So let's look first at coordination number, then we'll do how many atoms are in there, and then we'll look at the volume in terms of like radius and whatnot. So here's my repeating ones with the atom centers at the corners, right? So coordination number is the number of other atoms a specific atom touches. So focus on one atom. We're focusing on that blue one. So how many other ones does that touch? Remember, these are actually touching. We're just drawing the centers here. So it's going to touch the one to its right, the one to its left, the one above it, the one below it, the one behind it, and there's another one. If we drew these other 4, if we drew 4 more cubes, it would touch one more in front, right? So I would have another one in front. So a total of 1, 2, 3, 4, 5, 6. That's why the coordination number for a simple cubic unit cell is 6. Each atom is touching 6 more. 1 in front, 1 behind, 1 above, 1 below, 1 to the right, 1 to the left. Kind of if you're standing there, picture somebody on top of you, 1 below you, 1 in front, 1 behind, 1 left, 1 right. Pretty easy to do, right? So now what I want you to think about is how many atoms would be in a unit cell net and what the volume would be. Let's focus on that. All right, let's see how many atoms are in here. Like I said, it takes 8 cubes so that we can get this totally connected, which means a corner. All right, how many atoms are total inside this unit cell? Each corner atom is shared by 8 other unit cells. So it counts as 1/8. So that's the way you look at it. So each corner is 1/8 of an atom. Well, how many corners are there? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 corner atoms, 1/8 of an atom each, because it's shared by 8 cells. So 1/8 times 8 is 1 atom, right? So a simple cubic unit cell has a total of 1 atom, just in 8 pieces. Hey, we could calculate, we could use Avogadro's number to convert to moles, use the atomic mass or molar mass, grams per mole, and we could get the mass of a single atom that's in there. Oh, now let's look at the volume. So go ahead and draw where they're actually touching, and let's take a look at what the volume would be in terms of like the radius. Now let's look at the volume. Okay, so here's the simple cubic unit cell. Edge length is L, and it's a cube, right? So L times L times L. Would you agree the volume of a cube is the length times the width times the height? So it's L times L times L, or just L cubed. Yay, we love the cubic ones. Those other 6, not so friendly. All right, so let's take just the face of this, blow it up where you actually do like a space filling model, so you can see that atom and that atom are actually touching where the little dots are the centers, and that atom and that atom are actually touching, that atom are touching. So you form that face of it with only 1/8 of that atom actually inside the cube, right? Well, you can see that they're touching, right? So can you see from this that the edge length is just the radius of this atom plus the radius of that atom? Would you agree? So the edge length L would just be 2 times the radius. So what we could do is we can calculate the volume of this simple cubic unit cell if we know the edge length, right? Or if we know the atomic radius. Hey, right? We're going to do a video on X-ray diffraction later where we can actually measure these experimentally in the lab. All right, so we got coordination number, right? We got the number of atoms in the unit cell, right? So coordination number was 6. Number of atoms in a simple cubic cell total was 1. And then the volume, which we know is L cubed, that's true for them all, but the edge length is equal to 2 times the radius. Let's take a look at the next one. Let's do a face-centered cubic next. You ready for the face-centered cubic unit cell, or just FCC for short? This is one of the more common ones out there. So a lot of the solids, metallic solids, are FCC unit cells. So think of the simple cubic unit cell, right? What we had, where we had atoms in every corner, but now we have an atom in every single face as well. So it's like if you take a dice, like a six-sided die, but you put a 1 on every single side. Ha ha ha, that's what it would look like. All right. So I drew the corners in red and the faces in green. All right. The way we can look at it. And if you blow up just one face of it, all right, you can see it from here where you've got the atom in the face, and then it's actually, this is the space filling model. So you can actually see the atom on the face there. It's touching the atoms in the corners. So I drew that, but you can see it's just touching that one portion inside the unit cell. So that the corners, remember, only 1/8 of the corner is actually inside. But if you look at the face, it's cut in half. It's shared by 2. So if I put 2 together, boop, that one atom hiding right in there is shared. Yeah, every atom on the face is shared by 2 unit cells. Boop. So a face atom counts as a half. We'll do that in a second. But let's look at the coordination number, right? So we're looking at, let's just take a look at this one atom right here. You see how it's touching those 4 in the corner? So there's 4 right there in that plane. So let's look at atom number 5. So this would be atom number 5 in green. That's the one on the face that's facing you. So you got 1, 2, 3, 4. It's touching the 4 in the corners, right here, here, here. So that's 4 in that same plane. But it's actually touching the ones in the faces behind it. So you see that one we're looking at? Well, it's actually touching this one, this one, this one, and this one behind it. Those faces behind it. So that'd be atoms 1, 2, 3, and 4. So it's touching 4 in the same plane, the corners, and the 4, the faces behind it. And then if you drew, right, it's touching the 4 behind it and the 4 in front of it. So a total of 12, right? So it's touching the corners, 4 corners, the 4 faces behind it, and the 4 faces in front of it. This will make more sense a little bit later. We'll look at it. We'll rotate it a little bit and look at it in a different way, which may be easier. But the net result is you've got 12. So what I want to do now is take a look at how many atoms are inside this particular unit cell. So let's do number 2. So number of atoms in an FCC unit cell. Let's apply the same thing we did for the simple cubic unit cell and then add the face, right? So we've got the 8 corners, correct? So we've got 8 corner atoms times 1/8 each is 1 atom, correct? Plus we've got the faces. Now remember, a face, there's half of it. Do you see how there's 1/2 in there? So each face, and there's 6 faces, 1, 2, 3, 4, 5, 6, like a 6-sided dice, each counting as a half. Plus 6 faces times 1/2 is 3. So 1 atom from the corners total plus 3 from the faces. That would be, everybody agree? 1 plus 3 is 4. So there's a total, even there is not an entire atom in here, but if you take the faces, the half each, and the corners, the 1/8 each, 8 corners, 6 faces, that's a total of 4 atoms, right? So they're packed in there a little bit more. So they tend to be more dense, right, than simple cubic cells. So let's take a look at the volume. That's going to get a little bit tougher. It's not as simple as the simple cubic. We're going to have to do some Pythagorean theorem. All right, so let's look at the volume of a face-centered cubic in terms of radius r of the atoms and the edge length. Remember, volume is just L cubed. Right? And this is L. But see, with simple cubic, those were touching, weren't they? So the edge length was just 2 times the radius. But since that atom's in the face there, it pushes those corner ones apart so they're not touching. No! Oh, not so simple. So let's take a look at the face. And do you see that diagonal across the face there? Let's get our geometry hats on and let's draw that triangle between 2 edge lengths and the diagonal. Everybody agree? So we've got the edge length, that's one part of the triangle. This edge length, and those are going to be equal, but the diagonal across the face is not, right? That's not equal to L. So let's take a look at this triangle. And we've got L here, L here. Now, what do you see going across? What do you see going across? Do you see that we take that entire face atom, right? You take the entire face, the radius of that one, the diameter of that one, and the radius of that one, which means this would be a radius, 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 radius. So do you agree that that diagonal across the face would be 4 times the atomic radius? Oh, okay. So what I want you to do is take a second and look up how we can relate these. Right? We got a right angle here. Starts with a P, starts with a P. So take a second and do that, and I'm going to go write that theorem on the board. Did you get it? Did you get it? No, we got a right triangle, so that has to go with the Pythagorean theorem, right? It's got to, and I'm assuming you remember this. So here's that theorem. Let's do this in brown. So a squared plus b squared equals c squared. Remember that? So let's do the terms of these. So this would be a, this would be b, and the diagonal is c, correct? So in this situation, a squared plus b squared equals c squared. Therefore, L squared plus L squared, because a is L, b is L, c is 4r. So L squared plus L squared is 4r squared. The term 4r squared, Pythagorean theorem. Can we add those together? Certainly we can. So let's go. Or we could just go 6. Let's square the 4, right? So we get 16. So far, so good. So 2L squared equals 4 squared, which is 16. So let's solve for L in terms of R, the edge length in terms of R. So let's divide over by 2. So L squared will be 8R squared, right? 16 divided by 2 is 8. Therefore, if we take the square root of both sides, L will be the square, or let's just take R, times the square root of 8. Right on? So if we know L, right, we can just cube it. But if we know the radius, we can just take the R, radius times the square root of 8, and then cube that. We've got the volume. So again, coordination number is 12. Number of atoms inside an FCC is 4. And then the edge length is R times the square root of 8. Thank you, Pythagorean. Gets a little trickier with body-centered cubic. Here comes the body-centered cubic. This one might be a little easier than face-centered cubic in some ways. The volume, I think, is trickier. So you've got a simple cubic cell with an atom in each corner, and then you've got one atom sitting completely in the center. Boom. Right? So that entire atom is in there. That's easy to count, right? So that's a body-centered cubic. You've got one in the body. So here I drew in red the simple cubic, and then that blue one is that one right smack in the middle. Now, if we do a space-filling model, you can see that one gigantic atom in the center, and then you've got an eighth of an atom for each one there. So it's so they're not touching along the edge or the face. Oh no, they're touching along the body diagonal. I see the center. So if you go from this corner here across to the opposite corner, so you've got the 2 corner atoms plus the body-centered cubic touching across the body diagonal. That's a lot harder to do the volume. So let's do volume last. Let's take a look at coordination number and the number of atoms. So I think it's easier than face-centered cubic. Right? Well, coordination number should be easy. Look at the one in the middle. Right? Can you see it's touching the 4 above it and the 4 below it? See that? So this is just represents the centers, but it's actually touching those 4 above and those 4 below. 1, 2, 3, 4, 5, 6, 7, 8. Right? So you've got 4 above and 4 below. So we had a coordination number 6 for simple cubic. It's 8 for body-centered cubic and 12 for face-centered cubic. Okay. Now let's count the number of atoms, and we need to know how many atoms are in this 1 unit cell in order to get the mass, in order to get the density. That's why we're focusing on mass and volume. Well, again, you've got the 8 corners, which count as an eighth each, right? So we've got the 8 corners. Plus, we've got that 1 completely in the center. And that counts as a complete atom itself. So this would be 1 plus 1 equals 2 atoms. So simple cubic had a total of 1 atom. Body-centered cubic has a total of 2 atoms, and face-centered cubic had a total of 4. So you can see how that really impacts the density, right? Because the masses get larger as you go from simple to body-centered to face-centered cubic. Now the volume for this is harder because we're looking across not the face or the edge length, we're looking across the body diagonal. We're going to have to do the Pythagorean theorem twice. Get ready. Oh, get your geometry hats out. The volume is very, very tricky because remember, it's touching across the body diagonal, the corner across the center through that body-centered atom across the next one. So it's kind of an angle. It's not on the face like on face-centered cubic. So we've got a right triangle that goes from the front corner to the rear opposite corner all the way across. And then you've got this edge length, and then you go across the side face here. Right, so one of the lines goes across the face, one across the body diagonal, and one across an edge length. Oh, this gets complicated. Still a right triangle though, so we can apply the Pythagorean theorem. So we're taking a right triangle across the body diagonal. So we got to figure out now. Would you agree that this edge length A is equal to L? Right, that's pretty easy. But this is a face diagonal, B is a face diagonal, C is a body diagonal. Let's look at the face diagonal first. So let's bring this over. Let's look at the face. Let's look at this right here, and let's see if we can figure out what B is. You ready? So let's take a look at the face. So let's do this triangle right here. Okay, let's draw the face. And then this B is the face diagonal. And then you've got the edge length here and the edge length there, right? So you see that triangle right here? That's that triangle. So you've got the edge length here, and the diagonal across the face is the B in that right triangle. So let's keep the notations the same. So that's a right triangle, so let's apply the Pythagorean theorem. Let's go ahead and do that. So L squared, right, plus L squared equals B squared, based on the terminology we did, right? And we're trying to isolate what is B so we can plug it into there. What is B along that face diagonal? So would you agree this would be 2L squared equals B squared? So let's take the square root of both sides. So let's see, B would be equal to square root of B squared is B. Square root of this would be L times the square root of 2. Would you agree with that? So let's plug that over here. Let's do this in red. So B is equal to L square root of 2. So A for this right triangle across the body diagonal would be the edge length L. The face diagonal would be the L times square root of 2. Now we got to get what is C in terms of the edge length. And then once we have that, we can take a look at this in terms of the radius as well. Ready? So now let's take this triangle and let's bring that triangle down. All right? This is going to get squishy. So let's bring this triangle down. Where B, whoop, that's supposed to be B, not L. And that's C. Can we apply the Pythagorean theorem again for this right triangle? Let's do it. So a squared plus b squared equals c squared. So now we're looking at that body diagonal triangle right here. A squared plus b squared equals c squared, right? We know a, we know b. So this would be L squared plus L times the square root of 2 squared equals c squared. Let's see what c is in terms of the edge length. So we got to solve for c here. Okay, well, let's take the square root of every single side on here. All right. So this would be L. You know what? See if you can solve this yourself. I'm going to have you try to do this. Isolate C. What is C in terms of L? And then once you have that, figure that out in terms of the radius. We're going to have to use this to see that. Give that a shot real quick. Going to make you suffer. Did you get it? Did you get it? All right. Let's work this through. So this would be L squared plus, this would be square root of 2 squared is 2. So this would be 2L squared equals c squared. And then if we add these together, this would be 3L squared equals c squared. So take the square root of both sides. So c would be L times the square root of 3. So if we go over here, c is L times the square root of 3. So now we've got that body diagonal length in terms of edge length. What we want to do now is see where do the atoms touch, right? So in body-centered cubic, they don't touch along the edge here. They don't touch along the face here. They touch along the body diagonal. So take a second and see if you can see how many radii go across the body diagonal from here to here. And let's get L in terms of the radius. I'm going to need another board for this. Almost done, gang. So what I did is I redrew that body diagonal triangle that cuts from corner to opposite corner across through the body, right? So that entire body diagonal was C is L square root of 3, right? This one was across the front edge length here. So we're going across the front edge length. That's equal to L. And then the face diagonal, so we're coming across here, across the face, and then through the body diagonal. So that face diagonal was B is L square root of 2. So we did that on the last one. But now I drew the atoms in there in kind of like a space filling model like this. Well, where do they touch? Again, they don't touch across the edge length or the face. They touch across the body diagonal. And let's take a look, right? Well, this is a radius, 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 radius. So do you see how the body diagonal is the radius of a corner atom, the diameter of the body center, and the radius of this corner? So that corner is an R, that diameter is 2R, and then R. So would this make sense that this is 4R is equal to the body diagonal, which is L times the square root of 3. Ho, 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 ho. So if we want to rearrange that for the length, just divide both sides by the square root of 3. So L would be 4 over the square root of 3 times R. So if we know the radius, right, we take 4 over the square root of 3 times the radius, cube that, and we're done. That's how you do it. So we did simple cubic, face-centered cubic, body-centered cubic. We can do the coordination number for each, the number of atoms in each one, and we can do the edge length in terms of the radius for each one. Whew. That was quite a bit, gang. You got it.